I'm not a crypto expert by any means, but I originally found out about this because a friend was in a cryptography course and he had homework where he had to read a paper about this subject and he couldn't figure it out. So I got called over to spend all day figuring it out as well. And I thought it was pretty interesting. And the paper is called Security Flaws Introduced by CBC Padding Applications to SSL, IPsec, WTLS, etc. And so I guess I'll just start with just how you might encrypt things. There's at least two mainstream ways to encrypt. There's something called stream ciphers. And in a stream cipher, if you have a plain text, say P0, P1, P2, you just take the input and you encrypt one byte or one character at a time. But that's one way. But in a block cipher, what you instead do is you break up the plain text into blocks of multiple characters, and then you encrypt one whole block at a time. And so the most naive way you might think to do this is you have a block of plain text here, and it's made up of multiple bytes. You have another block of plain text, so on. And so you pass it into your encryption function, and it takes in a key, and then it outputs some ciphertext. And then you could do the same thing here. Now this is actually a really bad way to do things. It's called electric code book encryption. The big problem with this mode is that if you have two blocks of plain text that are equal, the outputs will be equal. So this is really bad. If you want to look online, there's this image of the Tux penguin that's encrypted using this method, and you can tell after the encryption that it's still the Tux penguin. And so this is bad. So there's many ways to improve this, and one of the really common ones is something called cipher block chaining, or CBC. And so what you do in CBC is, right here, before you pass in the encryption function, you do an XOR, bit by bit, with something called an IV. And this is a randomly generated number that's the same length as this. And so you just XOR bit by bit, and then you get something new here that you encrypt with using the key, and you get your first block of ciphertext. And then you don't use the IV here again because that has the same problem. You grab this and you put it over here and XOR it too. And you do the same thing all the way down until you reach however many blocks you need in order to encrypt your full message. So this covers one of the things involved in blocks cryptography. The other problem, though, is that you need your blocks to be completely filled out. You can't have the final block be shorter than the rest, because most encryption functions require that it be a certain size. And so this is where something called padding comes in. So padding, you just attach something onto the end that can be recognized as padding, and then you encrypt that. Same thing. So the padding that we're going to be discussing here is just, if the padding is of length 1, it's going to be a 1. If it's of length, if you need to add 2 bytes of padding to the final block, you're going to have a 2, 2. And then 3, it's going to be 3, 3, 3, etc. So once you're done decrypting the full message, it's easy to detect what the padding is and just strip it off of your message, and you've got back the original message after decryption. So I'm going to input this space. So now we're going to define something called a padding oracle. A padding oracle is defined as O of C. That's really messy. O of C. So if C is your ciphertext, O of C is equal to 1 if the padding is correct in the decryption. In decryption. And it's equal to 0 otherwise. And so this is basically, for any ciphertext that you give it, it will tell you whether the original plaintext had correct padding or not. One way that this might work in the real world is if, say, when you're going through the decryption and padding is incorrect, maybe there's a timing difference. Or maybe, since some programs have done this, they just tell you, oh, the padding was incorrect. Either way, if you have access to this kind of oracle, or you can derive some sort of oracle like it, it's actually possible to decrypt the whole message without having access to the secret key. And so that's kind of concerning, and it's broken a number of applications over the years. And so I'm going to try and show you how it's done. So first what we'll do is we want to define a last byte oracle. And so it's a bit simpler than this. All it's trying to do is, for any given block, it wants to find what the last byte was in the plaintext. So let's say that you have some ciphertext Y that you want to decrypt. What we'll do is construct some other string that's RY, where this is concatenation, it's above. And we'll want to pass it to this magical oracle that we have access to. So what this is, R is a single block, and Y is a single block. Because we're going to decrypt like one block at a time. So Y is one block. So you could say that this is Y, for instance. And then R is something that we've constructed. It can be completely random, and it will be like this. So this is just some message R concatenated with Y. Yep. And so, yeah, we want to know if this has a valid padding, even though we just chose R completely randomly. So what we'll do is we pick some R, and if O of R concatenated with Y equals 0, we'll throw that out, and we'll pick a different R. And in that different R, we'll make sure that we change this last byte. And by changing that last byte, we'll get a different value coming into here. And that means that if you're going backwards, and you have all of this information, you get a different value up here. So what this means is, if O of R concatenated with Y equals 1, then this has a valid padding on the end. Now, you look at that and you say, well, okay, it's a valid padding, but we don't know if it's 1, if it's 2, 2, if it's 3, 3, 3, etc. So it's not actually equally likely that it's all those possibilities, though. The reason is because if it's 1, then you only had to get a single byte correct. If it's 2, then you had to get both of these bytes correct. If it's 3, you had to get like 3 bytes correct. And so if there's like 256 possibilities for a byte, you had a 1 in 256 chance of getting this one, a 1 in 256 to the power of 2 chance for this, if it's 2, 2, etc., etc. And so most of the time, what you'll find is that when you pick a random R, you'll get some padding up here of 1 once you find some that makes this oracle produce 1. And now there's actually an algorithm to determine like what exact padding you've gotten. It's a little more complicated, and although like I could figure out like how to implement it, I couldn't really justify why it worked. But but anyways, I think that probabilistically this is pretty good. You can implement that algorithm or look it up and figure it out for yourself. But let's just assume that this had a padding ending with 1. Oh yeah. So if for a random r we get a padding of 1, then what we can say is, let's see. Let me just write it down first. So let's define the text that we get here as A, and it's A1 dot all the way to AK. And so this will be P0 all the way to Pn, and so I guess for this drawing that doesn't have any dots, we'll just you can just say that this is like Pn minus 1. And then if we're not using R and Y, but we're just using the actual ciphertext that we had, this would be C of n, or we could call it like Y of n, and then this is Y of n minus 1, or C of n minus 1. And so what we can say is that this equation is where this is Pn of k. So the final byte is equal to this final byte XORed with this final byte here, plus the padding that we generated, which is 1. And so what we've done is we've actually decrypted the final byte of this block. And it's just that equation. And we know what C of n minus 1k is because we have the complete ciphertext. We've just derived this number. And so, yeah, we have everything we need to get the final byte. And so from there, we want to move on to decrypt a whole block. So the basic idea is we've generated a 1 here before. Now we want to generate a 2. And now this will no longer produce a valid padding. But we'll make some new R to concatenate with the Y that we had. And we'll use our oracle again. And we'll keep generating R's until we find some new R that makes the oracle produce 1. And what that will tell us is that we have found a 2 in this spot, because that's the only way that the padding could be correct. And from there, I'll come back to this in a second, but you can see how this will keep repeating, so that we then change this to 3 and 3, and we'd look for a 3 in this spot, producing new others. And so the actual algorithm is something like this. Assuming we have a J all the way to a B, So okay, so I wrote B in my notes, so let's change this to a B. Some J less than or equal to B. So these are the how far we've derived already. To get a J minus 1, a J minus 1, add. So we take OK is equal to AK XORed with B minus J plus 1 for K equal J to B. And so this is incrementing this padding by 1. And so it goes from like 1 to 2. And then pick R1 to J minus 1 at random, and take some value I equal to 0. Take R equals to R1 J minus 2 J minus 1 XOR I, and then RJ all the way to RB.
So is this the algorithm for deciphering, or?
This is the algorithm basically to do this implementation.
Oh, so to create the pattern.
Yeah, we're basically showing like if you have AB, how do you get to AB minus 1 in a more formal way? And then if the oracle produces 0, then go to step 3 and increment I. And then what you get is output J minus 1 XOR I and so now using this we can decrypt this whole A, and using the same trick that we had with figuring out the very first plaintext, we can now figure out what the whole block is of plaintext. And so from here, it's very simple to see how you decrypt the entire message. If you have like some long chain of like ciphertext, you just cut it off and pretend, oh yeah, this is where the ciphertext stopped, and continue on. And so now you've decrypted the whole message using nothing but knowledge of whether the padding was correct for some ciphertext that you generated. So there's a number of ways discussed in the paper for how to solve this that all don't work, and the authors discuss why all of them seem good but then fail.
Basically, the algorithm to write the code based on the fake input that's produced by the hacker, right?
Yes.
So the hacker creates these customized blocks of data, feed it to the algorithm, and then to see what it gets, but based on the error that it receives.
Right. Based on the error of this had a valid padding or this did not have a valid padding. Yeah. And so in some protocols, like if you can remove the timing attack entirely so that there's no timing information on whether the padding was correct or not, then you can avoid this issue. Another way to do it is to you basically pad the message like normal, and then you put a message authentication code or a digital signature or something like that on it, and then you pass that along to the receiver. And when you're decrypting, you have to check whether the authentication works or not. What you can't do though is authenticate the unpadded message and then pad it, because then you'll have a different message and it's no longer authenticated.
So, but there is a question here, because when a hacker wants to hack a secure connection, they don't have direct access to the server. They have access to the traffic, right?
Yeah.
So when the server or the encryptor or decryptor on the server generates an error, how the hacker receives that error message? They just reject the connection.
Yeah, but it might reject the connection quicker if the padding is incorrect than if it's not incorrect. So that's one way. And there's also been, I believe it was a protocol for cellular phones that actually just told you, oh, the padding is incorrect. And so, yeah.
One of the approaches that I saw with the whole SSL v3 thing was assuming you have some sort of cross-site scripting, where once you have that, you can send messages to the server from, but actually you don't even need that. You just need to have page loaded from the user, and so you can send SSL requests to the server using JavaScript, and then monitor the responses.
One thing can be done is when the data is incorrect, well, there are two ways. You can either don't reply at all, so you keep them guessing, and at the same time trigger a red flag somewhere, so someone gets to take a look into it. Or you can send random data, so the hacker starts to figure out what it is. At the same time, the red flag is raised somewhere else, and someone is looking into it. That's the way you can deal with it.
Yeah, that will sometimes work. You might not always be hacking some server. You might just be like trying to get into a device.
Yeah, but you have. Do you have physical access to that device?
Depends on the situation.
What are some of these methods that don't work? I'm excited to learn non-methods.
Oh, I didn't study them too closely.
Oh.
I'm like, oh, these don't work. This is
Okay.
I can give you the paper if you're that interested.
Yeah, no, I'll definitely look that up. Because it's...
Any other questions?